Okay, so our next topic is next presenter is Deral Heiland. A look at cellular services and IoT technology. So it sounds pretty interesting, combining IoT and cellular services. So his abstract with the submittal growth of IoT technology continuing from industrial enterprise, medical, consumer to transportation IoT, there has been an expanding need to connect these devices no matter where they may be located. To solve this problem, we have cellular technology to the rescue. During this presentation, we're discussing various types of cellular services most often seen in IoT. We will be reviewing potential security risk impact along with examination of various vendors and products at the component level that are available. Also, we'll be discussing various methods and concepts of how to approach evaluating the security of devices leveraging the cellular technology. Daryl's background is he's a principal security researcher of IoT for Rapid7. Daryl has over 25 years experience in information technology field and has held multiple positions including senior network analyst, network administrator, database manager, financial systems manager, and senior information security analyst. Over the last 15 plus years, Daryl's career is focused on security research, security assessments, pen testing, and consulting for corporations and government agencies. He's also conducted security research on numerous technical subjects, releasing white papers, blogs, security advisories, and presented the information at numerous national and international conferences, including Black Hat, DEF CON, ShmooCon, DerbyCon, RSAC, Hack in Paris. That was probably fun. You know, Daryl's been interviewed and quoted by multiple media outlets and publications, including ABC World News, Cheddar TV, BBC, Consumer Reports, MIT Technical Review, SC Magazine, Threat Post, and The Register. Man, woo! You're a busy guy. So let's welcome Deral for his presentation, and looking forward to hearing about IoT and cellular with the merging of those technologies. So I know Deral and I kind of go back. Oh, just a little tidbit. I was going to maybe wait till afterwards, but I thought I'd throw it out here now. So Deral is one of our founders for Ohio Information Security Forum. So you guys are here because of him. So wasn't you? So just so OISF has been around for 15 years, and it's part of the Deral putting that together. So thank you for allowing us to be able to continue this for you. So, all right, I'm going to switch this mic to you, and then it's all yours. Yeah, you can take Adrian. That's it. That's his problem.
If I trip over these, I hurt myself.
Blame Adrian.
I will help you.
Tried to clip it on my mustache. Does that work for you, Adrian? You got it? Good. So I really don't like having this much electronic gear strapped to me. But, so I am old. Probably the oldest person in this room. So again, a look at cellular technology in reference to IoT. So this is a project that's kind of been on my table for a while. Obviously, this is not a conclusion of it. This is going to be more of an introduction to it. So we're going to bounce through a number of topics. I might digress off onto some things in the process. I apologize for that. If you think, why the hell is he talking about that? But it is what it is. So the goal here is to talk about cellular technology that we see showing up in IoT technology and the security of that. One of the things in my project is to expand out to get a better understanding when we're trying to review IoT technology. Often I want to understand what I refer to as the end-to-end view or end-to-end security of IoT technology. That's looking at the IoT technology from the end technology to the cloud services to the mobile, the entire ecosystem. And one of the things we find out is as some of the security methods get better, we get better at encrypting Bluetooth and Wi-Fi and internet communications and things like that. How do we get insight into what kind of data is flowing back and forth? So this is kind of spin-off of my interchip communication analysis work that I've been doing, which I'll reference in this and actually shoot you or have a link to the paper that I released on that. So again, this just happens to be another component that is in the embedded hardware of technology. And we want to understand what that means and how do we look at it. If communication over LTE, 3G, 4G, 5G is encrypted, and I can't legally capture that data, how do I know what's going back and forth in that channel? How do I look at what's at the other end of that channel? Well, we're going to talk about how we're going to do that today. So next. So again, here's some contact information. Feel free to reach out to me. It's my Twitter, my email address. So if you have any follow-up questions after today, again, do not hesitate to reach out to me. I'm very open and I will answer you. If you reach out to me and say you're a fool, I may not reach out to you. But short of calling me names and throwing rocks at me, I'll definitely reach out to you and answer any question you may have. Because the ultimate goal is knowledge and knowledge sharing. That's one of the reasons why I do this type of stuff. Click. That works pretty good. So introduction to IoT cellular. So the two areas that we're going to be talking about is NB-IoT and LTE-M. A little bit. We're not going to go deep into it. We're going to and then we're going to dive into some of the more cool things in reference. Most of these standards are all driven out of what's known as 3GPP, which is third generation. Oh gosh, I'll never get it right. Third generation program something. It's a conglomerate of 7 standards organizations out there that are working together to define all of the cellular communication standards. Why? Why do we have NB-IoT and LTE-M? There's 3 reasons here: size, cost, power. We want to be able to communicate from a remote device, and we have limitations. We have limitations of size. So we need to be able to have technology that's physically small. We also have to have technology that is cheap. You can't have micro technology and have it cost you hundreds of dollars and then drop it into a consumer grade IoT thing and expect to be able to market it. And the third item is power. We want things that are low power consumption. Often IoT technology is sending out, let's say, telemetry information, as an example. This could be whether it's automobiles, medical devices, airplanes, name the list, consumer goods, all of those type of things. They need to be able to send this data out, and it's often not massive streams of data, telemetry information. So you can actually make the devices small, cost-effective, reduce power. Literally, you can take devices that are battery powered, that have low telemetry requirements, and get years, upwards of 10 years of cellular data transfer based on it waking up and sending out a short burst every so many hours or once a day. And we need devices that can do this. Again, small, low power consumption, and cheap cost. So most of the devices I've actually looked at vary in price, the cellular devices. The funny thing is I was out this weekend and go, hey, I need to buy some more of these cellular modules. And I'm looking at these specific ones and they're like, this is like $50. This one's like $60. But I can go buy a freaking device that actually has it in there for 20 bucks. It's kind of funny, but click. Okay, so the first one we talk about is NB-IoT, or narrowband IoT communication. The interesting thing with a lot of these particular devices is the naming standards. So I call it NB-IoT. It's also known as NB1 or NB2. There's variations of it with different speed and requirements of that. You will also find references of other things out there that mean the same thing. So when I went out there months ago trying to do research and figure out what are these two standards, it seems like every paper I would read on it would call it something different. But in general, NB-IoT or NB1 and NB2, there may be other standards in the works, NB3 or whatever the case may be, but that is the case. So typically on communication, there's 3 modes on these things for NB-IoT technology. One of them is standard LTE band. So it's going to go out over standard LTE band. So as we're talking about these 2 standards here, this is irrelevant of whether it's 3G, 4G, 5G. These all can be piggybacked on every one of those overall communication standards. The other one I thought was really cool is called guard band. So when you start talking about LTE bands are basically stripes of frequency bands. And the space in between them is known as guard band. So it can actually be deployed and use the unused bandwidth between the LTE standard bands or the guard band areas, as an example. I don't know who's using that. From what I've seen so far, most of the implementations that I've messed with AT&T and Verizon, both appear, at least so far from what I understand, to be using standard LTE in-band communication. But the standard will support that. And then standard, in the case with standard, that is standard digital channels that are actually used in LTE. Power. These devices have these 2 standards. One's called EDRX and PSM. Basically what these standards do is give you the power saving capability. The devices, like your cellular phone, is constantly connected to the cellular service and pingy. It is burning power constantly, because if it didn't do that, your phone would probably work much longer before the battery would go dead. But on these devices, you can't do that. So you have to be able to power these devices down. So one of the standards basically how's it capable of powering down when it's not in use. The other standard creates an environment where connectivity, so that you don't have to rebuild the connection channel, stays intact. Okay, so you don't have to go through the power consumption of establishing a proper channel communication out onto LTE. It will immediately connect right up. Because one of the examples I use is devices I've messed with that tried to use this similar concept without having this capability in Wi-Fi. There's devices that will do that. So they'll Wi-Fi out to your Wi-Fi network and then they'll shut themselves down. But if you ever watch those work, those things take forever to connect up and consume all kinds of power because there's no maintained channel functionality. And it's the same way in the cellular world. You want to maintain that a structured channel connection so that when power is applied, it easily has established connection or can establish that connection quicker and more efficiently.
So it's going to work mainly for a stationary application, I presume, since the tower would have to keep that channel available.
Yeah, typically, it comes down to what LT, and that's actually true. But it's going to come down to if you're dealing with most IoT, somewhat stationary. You know, if you have something in your house, you have something out in the field, you have something industrial, it's in place, it's going to stay there, so that's capable. When you start getting into like vehicles, cars, that may be a little different, but also in a car or vehicle, you have the power capability to maintain more power on the device. Plus, even when your car is shut off, I assure you those things are still talking. So in those cases there, even though both NB-IoT and what we're going to show here in a minute are capable of being in automobiles, the automobiles may actually, because of higher bandwidth of telemetry data, may use other capabilities or other chip functionalities. But I actually believe a lot of the automobiles use what we're going to talk about next. But I cannot confirm that. I only base that on a guy I know at work that actually hacks on automobiles, talking to him about the particular chipset on cellular that he described to me in his device. Click. So again, here is basically the standards of NB1 and NB2. or LTE Cat MB1 or LTE Cat MB2. There's another naming standard, as I told you. You'll have all these weird acronyms thrown in there. And you can see the download peak rates are very slow on these. So you second column down, you can see how slow they are. Also notice the latencies, 1.6 to 10 seconds. These are devices that are not real time, but they're devices that need to be able to supply some kind of telemetry data up to some kind of cloud services. These are only half duplex also. So again, and if you take that whole narrow bandwidth, minimum amount of data, the latency, the ability to handle the power consumption, low power, you can imagine one of these devices dropped into something, put somewhere, could run off a battery for upwards of 10 years, they're saying. Of course, this comes down to the quality of the particular chip that's actually being used. Click. The next one I want to talk about is Cat-M, or LTM, or Cat-M1, or Cat-M2. So we make sure I get all the different nomenclatures on the same screen. And you may actually find more. Again, the same thing, reading this up, you may find this with variations of these naming conventions. This is a very higher complexity. Go ahead and click. Should bring up that, there we go. So we can see that from the get-go. Very high complexity, lower latency. So we can see the latencies, 10 to 15 milliseconds, definitely faster. Something that would maybe be, telemetry data, but it also may be closer to, obviously you're not gonna, 10 to 15 milliseconds, probably way too slow for some things, but a lot of things that's very sufficient and should work fine. The mode of this is in-band LTE, so this isn't going to do any of the weird guard bands or any of that type of stuff. Again, this also has the power capabilities defined into the standard. Whether it's defined into the chipset that implements this is another thing that's up to the individual vendor. But we can see the bandwidth on this is much bigger, way much bigger. 1 megabit, 4 megabits versus 24K and 64K, I think it was. It's pretty amazingly slow. These are actually full or half duplex. So we have some of these devices. I think I have some of these devices here. Where did these devices go? Dang, man. I'm always losing stuff. Well, apparently I left it at home. But I had a modem here earlier. And I must have left it at home. But I had a Cat M1 cellular modem that I have been actually testing with over the last couple weeks. So I have both of these standards in my lab. So I have SIM cards for both MB IoT and Cat-M standard. Both of them are 1 series that I actually bought. So these services are available from like Verizon. You may actually see these used in trackers, especially the MB IoT. These things with a low latency and all that type of, it can get pretty good ranges on these things. So, you may have a GPS tracker you slap on your cat or your dog. This is probably the typical type of SIMs you would slap into that. I think you probably want to do Cat-M1 because if you're like GPS and a dog in a full sprint, with a big latency on the other one, you may not even be close to where they actually were. But if you're tracking and you're just tracking movement, it would store that data and send it in burst traffic to improve power consumption and functionality and things like that. So, click. Any questions? Gosh, I don't like quiet.
So what about like the new Apple thing? Like I had like that X-Wire for a minute, like in terms of tracking, which did not work for me at all. But it sounds like the one that Apple has come up with.
What is it? Yeah, explain it a little more.
What are they called?
Tags. Often the tags are actually synced to your phone. And what they do is they do cloud sourcing on a lot of those tags. So the more people that have that service on your phone, those tags will connect to their phone. So if you lose something in a city park, and then you can go online and find out where it was, two things: you either find out the last place your phone was connected to it, or it'll connect to someone else's phone. And that's mainly how a lot of the tags work. And it's usually Bluetooth low energy to your cell phone. And your cell phone provides the GPS data that's sent up to the cloud service.
That's why the Apple tag works better than like that XY thing that I bought on Kickstarter. It never worked for me.
Yeah, there's a number of different tags out there, but they utilize your phone, and them themselves don't. Most of them don't have cellular services. The cellular services, the two cards I bought, the MB IoT and the other one, are both lower. So I get 2 terabyte of data transfer for a year. Okay? But I think the MB IoT one I have is like 24K hertz or something like that. The M1 that I have from AT&T, it doesn't go up to 1 meg. The one I have only does, since it's a fixed service for low bandwidth usage, I think it's like 56 or 64K. It's still low too, but it costs $30 for a year, and they'll function for an entire year. So those are typically what you're going to buy for most GPS trackers, simple watches. When I say simple watches, it would be simple GPS stuff or data telemetry stuff. If the watch actually does cellular, you can make phone calls and stuff on it, then no, you're not going to be able to put these on here. Plus, when you buy these SIM cards, you're required to actually swear allegiance not to use them to like make phone calls or attempt to make phone calls. But they shouldn't be phone, they should only be data. But they also don't want you like surfing the internet on them either. And they make those statements. But yes, sir.
Are you mainly seeing these as like just outbound telemetry style, or do they have like quote-unquote C2 within that?
Well, I mean, I think they can come back in. This is kind of early in the research, so I haven't looked at too many devices. Like I said, I have the cellular modem, which typically is connectivity. So I can bring stuff down and I can send stuff up, but it functions like a standard modem. I control all of that. The other device that I actually have here that we're going to talk about, look at some stuff in reference to that, happens to be Simply Secure home security system, which has cellular capability within that. Now, does that handle both ways? I think it probably does, based on some of the functionality. I don't know if we'll see it in some of the data I captured here when we show this, but I think it may have that capability. Now, the device that I played with just started on the Thursday afternoon, okay? Because I knew I had a team working on doing home security systems this last year as a training exercise. And when this thing spun up, I'm like, hell, I think those ones had cellular on them. So I called them up and like, hey, you still got that device? They're like, yeah, ship it to me. So it didn't show up until Thursday. So they're not configured. So what we're going to see later during this presentation, there's a high probability you would see way more interesting data, but these were never ever configured. So I'm looking at just out of the box, powered up type stuff, and trying to basically prove a point here around how we would approach security, not necessarily trying to show some problems with anyone's product. Click. So we're going to get underneath the hood a little bit. So there's a number of modules out there. No way does this include all the vendors. There's a number of other vendors. But these are the ones I typically see. Quitel, uBlocks, Sierra, Tellight. I've worked with all of these but the Sierra. The Sierra ones you see very much coming from stuff you buy from China a lot of times, cheaper stuff. But most of these modules are fairly cheap, and they come in every flavor that you could ever imagine or capable. So if you have an idea of what you want to do, there's a chip for it, okay? So why? Why are chips sold this way? Why can't you just build this into your device? The reason why nobody does that is because then you're going to have to take your device through FCC validation checks. If I put a module on the device, the module's already been validated by the FCC. I don't have to do that. So that brings up and answers the one big question. How come it took 1.5 years to 2 years before we actually were able to use 5G? Because there was no one manufacturing modules. Even though chips were beginning manufacture, there was no one manufacturing modules. And no one's going to go through the headache of producing a product that they have to have through FCC. And that's right out of the mouth of the vendors, because when this all hit the fan, I was not this year, the year before, I was actually at the Consumer Electronics Show in Vegas. So I spent a week in Vegas at the Consumer Electronics Show, and I talked to a number of the actual chip module manufacturers. And they were complaining that there wasn't any 5G chips available for them to produce modules yet. There were some, I talked to some vendors that were in the process, but they hadn't released them yet. And then I talked to people that were actually using the tech, producing cellular modems, and I'm like, why are there no 5G? Just out of curiosity. And they're like, you need to go talk to them. They're the ones producing the modules for us to be able to make the product function. They haven't done it yet. So that kind of explains that whole history there. So if you pop the caps off all these, actually de-shield these, almost always you're going to find Qualcomm chipsets. I've never opened one up where it wasn't Qualcomm chipsets. Typically the 9603s or 9606s or whatever. And of course all of those chips are basically OEM, so you can't get data sheets on none of those chips legally. Click. So we're going to look at a teardown, and this is kind of fun and knowledge. I've actually done work for chip manufacturers, not just cellular, other chip manufacturers that produce module units. And we're going to talk about some of the approach that I take to look at an actual chip or actual module. So click. So here is an actual, that module we've seen before, and this is with a de-shielded. This is actually FCC data. So I can go to FCC sites, and uBlocks is nice enough to show me what's underneath the hood. You go to Tellite, and it's all like blank. They wipe everything off, so you can't actually see the chipsets. But I know what the chipsets are. They're not kidding me. I can just buy one of these modules for $20 and take it apart myself. So this is kind of what it looks like underneath the hood. And this we have, the lower one here is a memory chip, and then we see like, 9206, the MDM 9206, is a common chipset coming from Qualcomm, and the other one's a memory chip. That memory chip, which we're going to touch base on here in a minute, not that it applies to this, what we're doing here, just because I wasted my entire holiday weekend with that chip. And I'm going to force you guys to suffer through it with me. That is a MCP. What's known as a multi-chip package. Multi-chip package is, remember, it's space, 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 space. Multi-chip package will contain both RAM, DDRM3, whatever, and it'll also contain NAND flash memory, all in the same package. System on chip is an entire processor, has everything, has your memory and the processor. There's no processor in that. There's nothing in that. So the interesting thing is those chips are very similar, and the first time I actually encountered one, I didn't have a data sheet on it and made an assumption. I assumed it was an eMCP, which is known as an embedded MCP, which is an embedded multimedia controller chip, which has a controller on it, but purely for just read memory. And after wasting many hours out of my life, I figured out, no, I was wrong, seriously wrong. But go ahead, next one. So what do we do with the chip? Well, the first thing I like to do with the chip is get rid of all those nasty components that are in my way. So ideally, throw it in an oven, strip it bare. This is my first approach. And what I want to do there is I want to actually identify, because we know what the backside is. We get the data sheet, and we know on the LAN grid array side where it connects to the board, we know where USB comes in. We know where UART comes in. Can I get to it from the top of the chip? Because remember, it's attached to the board, I can't get to it. Okay. So I often like to reverse engineer the actual component layout. This case, it didn't really help me any, but we at least do that to see if we can identify things like JTAG, serial wire debug, USB, UART connections. These are the 4 key things that I can interact with this chip. And if I can get to it from the surface in some bizarre way, that means less likely I have to take more crap apart. So this is purely a knowledge building exercise that I do a lot on components. When I get a module, tear it apart, especially if I start seeing it more than once, I start reverse engineering the module to see how it's structured, to see if I can make life easier for Deral down the road. It doesn't make life easier for me here because you're going to see this setting on a penny here in a minute. Click. Oh, that clicker's broken too? Okay. Okay, that's kind of hard to, it's kind of hard to, does it work? Okay, well, that's kind of hard to see up there, just mainly because of the screen. But the red, I can't even make it out now. Dang, it's really bad. Okay, I know the yellow is JTAG, the red is UART, and the purple, I believe, is USB. So that is underneath the microcontroller, which does me no good. And I was able to trace it out anywhere else. Is it working now? All right. But this is kind of this. Okay, so this is kind of how it looks like. This is the bottom of the chip over here. This is the land grid array. Land grid arrays are not ball grid arrays. They're square blocks and they're a pain in the butt, at least for me to work with because they're hard to put back on. BGAs are much easier in my opinion. And then over here, this is a surface chip with all the components. The goal is key things over here that I want to identify. Can I identify them on the surface of the chip? Then once I identify where they're at, can I get access to them? Because let's see if we can go backwards here. Oh gosh, there we go. As you can see, they're, oh, it's thinking ahead, man. Man, that takes time to catch up here.
It's your graphic.
It's the screen, yeah. No, you can see it changing over here, and then it takes forever for that 1969 computer back there to catch up. Oh, really? Okay. Okay. So you can see all these components are packed in here pretty tight. So the only way, you can't really get to the runs underneath here, but you could get to the resistors, the capacitors, things that have silver showing. And you try to identify, is there any attach point where I can gain further access for further analysis on a device once it's disassembled. So we'll get it going here. Based on how slow this is, the videos when we run these, I don't know if they're even going to work. But as you can see how small everything is. I'm sorry for that. I thought it would look bigger on this screen. This screen's kind of grainy to start with. But we try to track that data out. And in this case here, it was not successful in getting anything that we can attach to on the surface. 6 hours of my life's lost. We move on. So in this case here, man, that screen is really grainy. So as you can see, here's that chip on a penny. This is actually the memory chip sitting on a penny. So this is that MCP we actually pulled off here. Multi-chip package is 162 ball BGA, RAM, NAND flash, everything I mentioned earlier. Let's see what we get here. So this is what that chip looks like from the data sheet. And we can see everything that's in the upper part, the sky blue looking up at the top, is the NAND part of it. So this is Daryl's weekend. This is what I did for my 4th of July. Deral wants access to the flash off this U-Blocks. This is a U-Blocks memory chip on the device. So what does Deral do? It's like, okay, we got to figure out how to do this. So my holiday weekend. So we take the chip, flip it over, and we can see these are 0.25 millimeter pads. So the first thing I do is I actually identify all the ones that matter to me that are NAND flash. I don't care about the RAM, NAND flash. So we identify those there. The next thing we need to do is, now that we've identified that, I don't have a chip reader that'll actually read this chip because it's a 162 MCP and none of my chips will do, or none of my readers will do that. A reader to do this is about $1,500. A socket to drop that chip into is $1,000. So $2,600 just entry for one chip that I encounter once. I may encounter it again, I may not. Okay, but there we go. So what do? Well, I need to get my reader to read that. So I pull out the data sheet. I go through the data sheet. I identify it's a NAND flash chip. I identify its block sizes, its out-of-band layout, it's basically its structure, its voltage, everything I can about it. And then I go out and find another chip by the same manufacturer that happens to be on my reader. And I find one that is a TSOP48, which is a 48-pin chip. It has 48 pins that are external on it. So then what I do is, okay, we got it matched. Now what I want to do is, let's make my chip reader think this is the damn TSOP48. And I do this all the time, so this is very doable. So, but how do I attach to this? That's where it becomes a nightmare. So that's why we balled it the first time to put the balls on there. This is 40 gauge wire. This is all done under a microscope. 18 wires were attached to this. So we attached 18 wires to this chip. That was Saturday night. So I did that. Well, I stopped halfway through it because I'm like, you just have to stop. You know, I usually lay 3 or 4 wires and then go do something else at work and then come back, do 3 or 4 more. And usually it's 30 minutes of real work, but you know, it's spread out over 4 hours, 5 hours. So we kind of did that. And then it was like, okay, how do I catch this to my chip reader? Well, I build a breakout board. I build this breakout board to function to plug into a ZIF socket. I don't know if anyone knows what a ZIF socket is. Basically, it's a 48-pin socket where the leads stick down in it, and then you crank this lever down to hold them tight. And that's what's in the chip reader. It's a ZIF socket. So I build a breakout board. And then I literally wire that chip onto the breakout board. So here you'll be able to see what it looks like. Try not to bust the wires. But here is the do-it-yourself ZIF socket plug for a TSOP48. And then I wire that up using the data sheets of all the data lines and write lines to match up to the TSOP48 that I'm trying to mimic. And then I just tell the damn chip reader when it says, hey, that chip ID doesn't match. I'm like, ignore it. And instantly we were able to adopt all the memory off this chip that way. So not that it had anything to do with this talk, but damn it, I spent my weekend doing this. You guys are going to listen to it. Any questions about that? Okay. Let's see if we can get over here. Okay, so modular interactions. So how are we going to interact with these modules once they're in circuit? I can't even remember what these slides are going to actually do. So here's another thing. Here's one way to really get an understanding of interaction. Often, in some cases, I'll actually use a development board. So we can get manufacturers to actually produce development boards for their products. Now, it isn't like Daryl's going to go writing any kind of cool code or anything. I don't really care. But I want to understand how the chips work. And often we can do it with these development boards, which are a very efficient way of actually approaching, evaluating a product and looking at it. Plus, when I have a development board, if I ever encounter, which we'll reiterate this down the road, if I ever encounter an IoT technology that has the same chip or similar chip in it, or something close enough, I could take a development board, steal the functioning configurations off the IoT device, which we're going to show how to get that, and put it on a development board, which would give me access, just like this was a router, to the back end of the manufacturer that IoT's back end cloud systems. Just like I was the device, basically taking their device out of it. So the goal, and this is one of the goals I'm working on, how do we better develop testing methodologies to help vendors check their products? We go blind a lot of times. We make assumptions a lot of times. I don't like assumptions. My goal is to produce processes where we can actually do those testing. That's why, another reason why I'm doing a lot of this. Okay, so often these modules are interacting in two ways. When I say there's more things that interact with a chip, okay, are the modules. The ones I care about are either going to be typically UART or USB. Okay, so, and based on the manufacturer, either one of these, either USB or UART, can be used for command or data, or both. And it varies. And both of these are available in at least every module that I've actually looked at. When we start looking at USB, you could, based on the type of device, interact directly like a modem. A cellular modem, I can connect externally via USB and interact with the device. Or you can do it through interchip communications. There's 3 different types of interchip communications for USB that would be used on these modules. One is known as HSIC, which is known as high-speed interchip. High-speed interchip, it runs at a high-speed mode, and I think they're actually developing some faster standards than that. I haven't seen them yet, but it's a high-speed interchip. It does not have the, it follows the standard protocol pretty close. What it doesn't have, can't have 16 devices. It just sees one device. One device will connect up. It also has a link limitation of 3 centimeters. It's on a circuit board. If it goes more than 3 centimeters, then you know the chip that they're using is probably not using high-speed interchip. It's actually using standard. Okay. So when you get onto the boards, and I've seen some, I have one here, which was a project I was working on. This one here, this is a module here, a USB module here, or I'm sorry, cellular module here that connects in and has all the circuit. This one actually uses some impedance circuits to actually get past that to bump it over. But this one appears to be high-speed interchip on this one here. The reason why I say that is, well, I was trying to read it. And none of my stuff could read it, sadly. And I was having problems with that. But I've been working on that problem. I've actually picked up the hardware, and I'm looking at possibly seeing what the possibility of building high-speed interchip relays circuits. So basically relaying it out is one of the things I want to look at doing. But they also do standard. If they do standard, you can literally route the data off the board through a USB sniffer. I have one of those devices and back into the board again, and it should work. Give you the ability to see all of that data traffic. That's theory. I have not tested it. I've just managed to spend the freaking money. I haven't tested it in the real environment yet. And then there's UART, which is external and interchip. So you can have external UART connectivity to a device, but you can use interchip. And again, I mentioned that paper I wrote, which focuses really heavy on interchip analysis. And we're going to see some of this here in just a few minutes. And the one I missed was eUSB, which is embedded USB. Embedded USB, another interesting standard. Not quite sure. I haven't seen it yet. That's why it's in yellow in IoT-based technology, other than I've seen it in industrial. And I've seen eUSB standard utilized to connect to actual, drives, flash drive systems. So you have a flash drive that will have eUSB capability versus USB capability. And again, it's short range. The thing is though, eUSB already has standard chips available as relays. So you can buy a chip, dump it into the chip, it'll dump it over to standard USB, and then you put another one on the other end to take it back the other way, which is how it's typically done in like industrial equipment that need large flash drive systems that they multiply share, like on a truck or a lift truck or some kind of vehicle, which I've actually seen them used for. Any questions? I won't run out of time here. No questions? Come on.
Is the USB kind of like a proprietary still, because it's kind of using USB, but it's...
No, I don't think it's proprietary. There's documented standards out there, and it's all open. Again, I haven't seen it a whole lot. I just recently, I encountered it about a year ago, and then I started looking into it, trying to figure out, hey, when I'm looking at IoT technology, what am I looking at? Is it standard? Is it high speed? Is it ESUB? How do I tell? Am I going to have to tell by data sheets on the manufacturer, which is typically the only way to do it. I think the chip that I have up there, or the chip on one of these devices, or that thing I'm passing around, actually no, not that one, this one right here. Actually this here, let's see here, which we'll show in a minute. This one here, actually the USB is standard on this, and this is for the Simply Safe home Wi-Fi system. You can see I already tapped into the circuit, so. Yes, I should. So let's come over here. Here's the modem I had mentioned, the Multitech. I thought I brought it with me, but I can't seem to find it. So how do you communicate with modules? AT commands. And you think, really? Oh, hell yeah. And it varies from vendor to vendor, but there's some pretty intense structure in those. You can have file service capability, firewall and socket services, or can be set up and enabled. You can actually allow incoming connections, FTP services. You can move files, do firmware upgrades, bring it down, execute it that way. MQTT services, which I have encountered, didn't encounter on any of this research, but on work I'd done in the past, where the work I was doing, I actually captured the data or pulled the data out of the processor's firmware for talking to the actual cellular modem, which was out of scope in the test. They didn't really care, but it contained all the MQTT configurations to actually set up, authenticate certificates, everything back to the cloud services. So yeah, AT commands. It's kind of cool. They're easy to use. Everyone has their own manual. They're all, a lot of them are fairly standard, but we'll see some of it here in a minute. So here's some examples. Again, these is kind of crappy. So this is in the Multitech. So down here, we can see the AT FRWL, which is actually checked for firewall. So basically 0000 all across just says dump everything. It literally says dump, that means dump everything. So I would have had to put my home, so everyone wants my home IP address. It's right there. If you ever want to play with it, I don't really care. It's on the internet. I'm sure everyone else has. So I actually put that in there. I didn't test to see what it would do because I hadn't put a functioning SIM card in this device yet. Or at that time, I hadn't done it. So then I was wanting to play with file services. So you can actually create a file with ATCAN, MTM write. So I can write to a file system. And when you look at config devices that have been set up and configured, this is kind of like, I've seen this actually used as a way to store crap. So the vendor will say, hey, you know, we have all these configurations. Let's store them here, and then we can call them from there and then execute them. And that way no one can get it out of our firmware because no one's smart enough to type in a damn AT command. So
Just you, Deral.
and then of course here is me doing ATM or MTM list. They actually get the list file. So, and some of the more advanced chips I've looked at, you've seen, you can actually start setting file system security levels and access rights and all of this type of stuff. It's just kind of amazing based on how advanced the chip is. Most of these low-end NB-IoTs and M1s or LTMs don't see all that many advanced stuff. You may see, because in this case, it's really low bandwidth. So if you buy more higher bandwidth type modules and chips, then you're going to see more functionality built into them. And these AT command manuals, like I had one, it was like 300 pages on a chip. So massive amount of command structure on these. So interaction on the hardware. So this picture up here happens to be the Simply Safe. Now again, I wasn't looking to hack into anything. I was just looking to be able to try some stuff out and just get some baselines. And then we'll get this here in a minute. Here we go. But as we proceed forward, we're going to start off with, this is one of the tests that I did. So again, we go back into, we need access. How do you get access? In this particular case, we had a module. That's the module on the picture on the left, the right to it. It's been a de-shielded module that's sitting there. I can't even remember what brand that is. But it's a de-shielded module there. And we were wanting to identify AT or the UART and the USB. Since we couldn't identify it anyway, we actually off-chipped it. We removed it from the device. And from there, we were able to trace it out. So we can see where we traced it from the land grid array out to some actually impedance matching resistors. So if I tried to trace something like this out, I would have never identified because of the resistors. That screw you up every time. So you have the physical vision. So this gave me the ability to actually tap into it. And here's the actual module. This particular case, it wasn't successful only for one reason, is I totally smoked the base unit before I got to this point. Because everything I tapped in just had a damn 60 hertz hum on it. And I'm like, hey man, this red light's like red light all the time. It never goes green. So things do go bad. Yes?
Just out of curiosity, what is your methodology for tracing? Because it looks like that's a dual layer board. Are you using a multimeter?
Yeah, I just use a multimeter. Just use a continuity check on a multimeter, typically. That and visual. And in the paper I wrote, I actually discussed that. That kind of concept is kind of a combination of both. It's like you got a multimeter, but you also got to take into consideration multi-layer boards, components in the way. So you have to be able to trace through and take those out and figure them out. I think even in a white paper I get into, there was actually components in the way and I was wanting to tap the circuit. So we literally removed resistors and moved them to the other side of the board. In the actual test, so we could actually open it up and make it easier to tap into it, as an example. But that was kind of a failure. But as you can see, we actually, hot air, we actually removed the component, was able to trace everything back and then put it back on. And as far as I know, I was never able to 100% validate it's back on functioning. And there's a really bad, funny story with this. We got 5 minutes. I'll have to go here in a second. So when I put this into the oven, I forgot to take the SIM card out of it. So I opened up the oven, I pulled it out of the oven. I pulled the component off, it all cooled down. I go back in and I noticed the SIM card slot had all of this white stuff squeezing out of all the holes. So what I did was, I'm like, besides go, oh shit, I actually took a razor blade after it cooled, cut all of the stuff off that was sticking out and was able to pull what was left of the SIM card out. And then I actually cut the circuit out of the SIM card and rebuilt a SIM card. Just by using one of the SIM card resizing kits you can get. If you need to go to a larger size, I just took one of those and glued it into that, and it does work. The SIM card does. I validated that. But it's like that, one of those moments, yeah, I do this stuff all the time, and I'm still amazed at the absolute stupid things I do. But that's, but you can see this one, we tapped into USB, and I can't tell you which one's which, but USB and UART on that. Don't take the SIM card out, because I don't literally own that SIM card. It belongs to somebody else. I destroyed their SIM card. Okay, So interchip communication in the case of this particular device here, which was the Simply Safe, I think I may pass that around. We actually, you see the unit, cellular modem, primary unit modem. And in this case, it was nice. It was a cable. So we were able to actually cut the cable and get access to the UART and be able to tap into that. Shoot a few short videos. Let's see if we can get these going. We get through these videos.
Which one would you like?
Like, what's the name of them? Bring them up.
There's the Epthrin.
Not that one.
Not that one.
Which one's that?
Yeah. Good question.
Run that one. I don't know which this video is. We'll see how it works. I don't know how big of a delay it's going to be. See if you can get it on the screen. What was that about biohack?
You ever given any consideration to biohacking?
What do you mean by biohacking?
Real animals.
Modifying creatures? No. Okay, so what we got here is we were actually looking at this device. I think this is the one we captured in between. So as this thing kicks off, we're actually going to see the AT commands go from the base module over to the other module. So it starts off, we just powered up the single dot. This is all UART. In this case, it was 3.3 volt UART is the communication. Is it running? It's a delay, so it'll take a minute. It's going to delay. Let it go. It's going. So AT, and eventually you're going to see the whole thing kick off. Once this thing responds back and wakes up, once it wakes up, this thing's going to flood it with a bunch of config commands. In this case here, nothing's set up, but you get an idea of how it all works. Boom. So instantly, so you see the ATC REG 0.0. 0.0 means there is no cellular connection. 0.0, 2 is we're in the process of trying to establish a connection. 0, 3 means we've been rejected. 0, 1 means you have an actual connection. So in this case here, we can see some configurations. We can see the interesting thing is they changed the firewall config to 1111. They also, in some other stuff that I captured, they had also set up, in this particular case, those don't seem to have much information, but the SC are socket configs. So they start setting up socket configs and they've enabled ICMP. So once this thing establishes a connection, it's going to respond to ICMP connections through a socket that's allowed to the back-end cloud so they can validate it's up. So we know they're going to do that from the very get-go as soon as it would establish a connection. I assume a fully functional, licensed, Simply Safe contract, that way more stuff is going to take place here. So guess what we're going to do next? Not today, though. Okay, let's go to the next slide. Don't go to the...
Go to the next movie?
There's 3 movies.
Okay. Slide or
No, movie.
That one. The other one goes. Yep.
Okay, which one we just ran? That one? UART AT commands. Which one we just run? Bring that one up again. No,
Yep.
that was what we just ran. That one, shut that down. Okay, do this one. I cut 3 videos. We'll get through them here in a minute. I apologize, I run over. Blame it on them. Is it running? It's running. Okay, so here is another look at that same thing. We're doing the same thing here. Can't remember whether, oh, this one actually, basically man in the middle, we're injecting data. So we have the ability to control some of the communication, at least from a basic standpoint. Same thing we've seen before, we're connecting up. This is live right here at the same time. And then we have a a send field where we can actually send data. So once we establish a connection, we make sure everything's running. I actually use the board over here. You're going to see it here in a second. You'll see me reach in there, and we have those dip switches. I'm going to throw all the circuits. So I'm going to kill all UART communication to the base unit, and then I'm going to go through a bunch of AT commands till it establishes. Once it responds back to me, it'll start taking commands. So you see me over there messing with it, done messing with it. And you have to send these. We'll send these AT commands. You'll see here on the lower center screen, I don't know how many times it takes. Boom. Ignore that one. That one's trying to connect, but it's hitting against the wall. There's nothing there for it to go to. There it goes. So now it starts responding to me. And then I just cut and paste one of these commands over there. I think the first one, we don't need to go through all these before we jump over the other one to get the gist in there. I think this command here happens to be HTTP config. So boom, we get the information that tells us how this device can get back to the manufacturer, HTTP, and the port. So we get 9978 as the actual port. So now we have the ability to interact with this. But, go to the next one. There's more interesting things. So this does not work, just to let you know what I'm going to show does not work, but I want to show you what we have in the works or what's in the works. It doesn't work because of some weirdness in this environment, which we didn't take into consideration in the tool. We actually wrote a tool to proxy UART communication, interchip communication. I didn't. Matthew helped put that together at Rapid7. And Pierce Morgan, or Pierce, I never get his name right. Yeah, that's it. So we're going to open up a tool called a Karen proxy. A Karen proxy, a Karen is one of the Greek mythical rivers, but it's the only mythical river that flows between the mortal and the underworld. So that's why we named it that. So here we're going to go through, and we are actually setting up two basically FTDI devices that'll handle all the communications. So all the communications between this unit and its UART its cellular module will actually be routed through this program where we have full control over it eventually. So in this case here, we set it up. You can see the baud rate on this was insanely low on this device. I started off with 115/200, and I'm like, why ain't this working? That works on everything. It was like until I took a measurement and mathematically calculated it out. I'm like, 9600. So, and then we can also, let me see, we set delimiters. Delimiters, basically, we want to know when the message traffic, because most interchip communication does not have line feed carriage returns. Oh, except in this case, okay? And that seems to do some weird things because it doesn't seem to pick it up. Even though we set them, they kind of set them, they don't set them. It's just kind of weird. We'll have to go back and figure that one out. But we would set up the delimiters to say, hey, when you see this character, that means it's the beginning or the end of a data stream. So that's what we set up there. So it gives us the ability to set those. And in this case here, one of the key things is, remember, as we're communicating here, this device communicates to the modem. The modem communicates back to the base unit, and then the base unit sends more commands, or whatever the case may be. So what happens if we want to tell the unit that the device is in a condition other than what it is? We knew it was querying back with 0.0-0, meaning there was no connection. I actually got this to work, but I couldn't get it to work under a camera. It worked 3 times. I actually would tell it that it's 0.1. And we do it with this because we have real-time changing data in the flow. So here, replace set. We look for 32C30 and change it to 32C31. Or 0.0, change to 0.1. The device gets it back. It thinks the modem's up. It should respond back. What we did get was some changes did take place. There was a few things that went over that we didn't expect to see. Nothing great, but something different did happen. So in this particular case, I ran this. It was kind of funny. I ran it. it worked for me after, it took a while because it keeps ignoring the device for some reason. We're not sure. There's usually not latency issues with UART, so we're not sure why. But then it started working, and it worked for me a couple times. I powered it off, back on, it worked again. I powered it off, back on, turned the camera on, and it ran for 30 minutes, and nothing happened. So in that case there, we turn this thing on. So we set it up there where it says start. It'll actually start relaying through the application, all UART communications. We turn on watch, and we can see the data traffic. A is the actual base unit. B is the modem. So A to B, it's initial power up, and you'll see it come change here in a second. That there is actually AT with a carriage return, AT. It's starting to send ATs. It'll do this, and then you'll eventually get an AT-OK back from the other side, seeing that we're actually relaying communication on the actual tool. And you'll see it change from AB to BA. There, BA, now it's responding back. Now we can track all traffic and log it going both ways with this tool. We also have the ability to change data based on hex string to anything we want in real time. We also have the ability to capture and replay anything we capture in any direction we want. So this is a proof of concept tool. So ran over, we're all done. Any questions? Yes, sir. It don't work. I don't know what the question is. Well, typically, if they contain both, cellular's backup. Okay, so like a home security system, cellular's backup. The only time it's actually typically going to be used is if your home network goes down, and that they can maintain a connectivity because they're monitoring your home and your home security system. So that's typically how it works. But not all devices are meant to have a backup. They have cellular or nothing. Remote devices are like that. Devices that may be used like on, let's say, an oil rig or something like that in the middle of nowhere, or, you know, because these will carry a lot farther range than typical cellular too. Yes?
So your tool for interacting, there's a tool called Expect that's available under Linux and whatever, but it's designed to work with these kinds of streams of data. You can do that plenty, but it gives you the full single programming support and written expressions and all that other stuff. So you can use that as a another tool for kind of intercepting and manipulating.
Right. Well, in this case here, I went out and looked at a lot of different tools. There's a lot of tools that'll gather data and replay data, but none of them would allow me to actually cut runs on a circuit board and route stuff off and do pure man in the middle, and that's what we were after. So the goal here was pure man in the middle. Everything goes to the tool, and we manipulate it from there. And again, it's still just a proof of concept at this point.
Once you've done the TDI for in and out into a computer, you've got a computer in the middle doing the manipulation, or what are you using?
Yeah, it's just a VM virtual machine.
As the program that glues the two interfaces together is very, very mature. It's a product of the NIST.
I'll have to look it up. Thank you. What's it called again? Expect. Cool.
Okay, thanks, Daryl. Very, very, very informative. All right, so we're